Sam Gillie, EAH Secretary, explains why it is often said the slide rule took man to the moon, and he also explains its critical role in saving the Apollo 13 mission. He simplifies the logarithm math the slide rule uses that allows multiplication, square and cube root problems to be solved by adding and subtracting. He tells his story about how the death of the slide rule by the transition to the first scientific calculators impacted his last year in engineering school. He shows his 5 slide rules he used, including a circular slide rule. His talk includes a timeline on the transition from huge mainframe computers to mini-computers, to desktop calculators, to handheld calculators, and ending with calculator apps on our phones.
Aloha and welcome, everyone.
Aloha.
Yes, this is the October 18th meeting of Engineers and Architects of Hawaii. I am Barbara Rogers, serving as president, and thank you so much for coming and joining us today. Okay, do we have any announcements? I know we have one. Aaron.
I put this in the Zoom chat, but I was able to get a tentative date for another rail excursion trip out in Eva. And the date is going to be November 16th. And right now I'm on the fence between the 3 p.m. ride or the 12 noon ride. If you're interested in attending, or if you have friends that might be into that, it's a cool thing to do, a bit of transportation history and a nice little excursion out to get a bite of ice cream on that ride. So let me know as soon as you can. We've got a limited amount of slots. There's 14 seats in that observation car, and first come, first serve, I guess. Max got the first spots because he paid for the last trip and never showed up. So he's got a free seat or two. But yeah, let me know if you're into that. That'll be November 16th.
Yeah, thank you very much. It's a wonderful ride. We had it not too long ago, so hope you can all join us. First come, first serve. Thank you, Aaron. Okay.
Do we have our guests introduced?
Why don't you introduce yourself?
Hello, my name is Thor Mendez. I'm currently an intern at Hawaii State Energy Office, and I just started about 2 days ago. I'm a senior at Wentworth Institute of Technology in Boston, Massachusetts. My major is construction management, and I have a concentration in facilities management.
Okay, at this time, do we have a bit of humor from Mac?
Well, as I said, this is from Howard Wigg. He passed it to Barbara Rogers, and she passed it to me. So some of you may have heard it already, but for those in the far distant corners of the empire, it'll be new for you. And here's how it goes. A sweater I bought was picking up a lot of static electricity. So I returned it to the store. They gave me another one free of charge.
Okay, all right.
Okay, it's a great pleasure to introduce our speaker for today. It's our very own Sam Gillie. He's our EAH secretary and one of the pillars of this organization. He's retired Hawaiian Electric, and he is going to talk about the tool that took man to the moon and saved Apollo 13. It's a single tool that was essential to the moon landing and later played a critical role in saving Apollo 13 astronauts. So we're kind of anxious to have you explain the lost art of the slide rule. Sam.
The tool. Some people think when they hear about the slide rule, you may or may not have you've heard that saying that the tool that slide rule took us to the moon, and I added, and saved Apollo 13. But most people, when they think about this, the space and NASA, they think computers. They think NASA or maybe even Elon Musk these days. But in 1962, President Kennedy challenged America to put a man on the moon before the end of the 60s. And his famous quote is, "We choose to go to the moon in this decade and do other things, not because they're easy, but because they are hard." He also said, "There's no strife, no prejudice, no national conflict in outer space yet." And that's mostly true, but both Russia and the US have their military satellites out there now. Its conquest deserves the best of all mankind, and its opportunity for peaceful cooperation may never come again. The tool that took us to the moon, and of course I'm talking about the slide rule. This is the official slide rule astronauts were issued by NASA, a 5-inch Pickett slide rule made out of aluminum. The tool more than any other that took us to the moon and critical to saving Apollo 13. Computers played a critical role for guidance and calculating fuel rates and burns and whatnot. So they were very critical in the actual moon guidance system. And there's a very good YouTube video on the 1969 Apollo guidance computer as it guided the landing craft down to the moon. And it crashed a couple times, but it recovered itself. And they managed to land on the moon. But overall, in the big picture of things, there was a lot of engineering that was done for the space program, and it wasn't done by computers. I'll talk more about that later. This is my slide rule I got out of high school when I was a junior for advanced algebra class, 1967. It cost between $10 and $20. Very simple, only 9 scales and only on one side. This may be, I may have gotten this from my older brother or sister, so it may be 57 or maybe 60 years old. But to appreciate the slide rule, you need to know how it works. So let's do some math. And I think we're all kind of technical here, so I don't think math should be too much of a challenge for us. I always wanted to be a math teacher because my 8th grade teacher simplified all arithmetic down to adding and subtracting. That's all it is multiplication, division, square roots. It's all adding and subtracting. But we'll find out if I'm halfway good at being a teacher. And of course, there'll be a quiz at the end. Let's do some addition. Now, if you take 2 boards and you get, one is 0.693147 feet or 8 inches and 5/16 long, and the other is 1.386294 or 16 inches and 5/8 feet long. If you want to add them, you can find out how long they'll add up to, and that's 2 feet 0744 or 7944 or 24 and 15/16. And that's how a slide rule works. It adds special lengths to put the lengths end to end. Why? Because slide rules does multiplication by adding. Okay, exponents. I think of exponents as math shorthand. So 10,000 is 10 to the 4th, 1 million is 10 to the 6th. It's pretty simple. We don't have to write all those zeros. And if you multiply them, the long way is you write it down 1 million divided by times 10,000. You shift it over, drop all the zeros down, and you count those 10 zeros, and you got 10 billion. But there's kind of a shorthand way to do it, and that is adding it as 10 to the 6th times 10 to the 4th. We get over here at 10, 6 plus 4. And of course, you get 10 to the 10th or 10 billion. So just add the exponents. This is called base 10, but we really don't care about that. So add 6 and 4, and you get 10. So how do you multiply a slide rule by adding? So let's try something really simple, 2 times 4. How can we add 2 times 4? By making 2 and 4 exponents. But how do we do that? Well, we can express them as exponents like this. 4 to the 0.5 is the square root. So the square root of 4 is 2. So 2 can be expressed as 2 to the 0.5. And over here you have 4 to the 1, which means you have 1 4. So that equals 4. So if we write 2 times 4 with the exponents, we get 4 times 4. And then down here we add them 0.5 plus 0.1 equals 4 to the 1.5. And so guess what that equals? 8. I did have to check this on my Excel just to make sure that 1.5 to the 4th is actually 8. And of course it is. And this, you could call this base 4. But this, let's make it more complicated. Let's have another way to express 2 and 4 as exponents. So here we have this magical number e, and the logarithms for that are called natural logarithms. So if you get e to the 6.93142, that equals 2. And the natural logarithm of 4 is 1.386294. So the natural log of 4 is, as I said. But I think we've seen those numbers before. Gee whiz. Here's my board. So if we add those up, according to my theory, we should have the answer, which is 2 feet some odd inches. Let's write the equation out. Log of e of 2, the log of e of 4 equals, and we're going to add them together. And this, of course, looks like what we did before. We're adding exponents. And this is what we get. We add it up. And so what is e to the 2.79442? We all know that it's 8, and e equals this long number, 2.7182825. And so if you write it out, how do you figure this out though? How do you do that? There you go. You pull out your little calculator that you get for free, and you get it, and it's, of course, we don't have the full number here, so it's 8.0, and then we get out here and it doesn't quite add up to 8 anymore. But how did we used to do this before we had calculators? Well, we had log tables, and I know everybody, the older guys here, know what these are. These are the log numbers for 1 to 100. But there are books of log tables, and I found a PDF of one that has logs for 1 to 100,000. And all of those numbers were calculated by hand to create those tables. So back to our equation, and we get our table. This is the same table, but this is only the numbers 1 through 9. And if we look here, there's that 69314, but actually it has all these other numbers as well. So this is the log of 2 to 15 digits. Here's the log of 4. It doesn't have the 1 there, but the 1 is, they're trying to save on ink or something, I guess. So they didn't put the 1 there, but it's 13869,629. And 8 is down there, 2.07944. So we now know that 8 equals e to the 2.979442. So get back to my slide rule and my board lengths. We have my board length is 0.6293142. I'm not getting all those numbers right. We add it to the logarithm of 4, 1.38, and then that equals 8, which is the log of 2.79. So if we look closer to that, that's what it is. It's basically, this part is the log of 2, this is the log of 4, and you put them together and you get the log of 8. You add it up, so that's it. And if you actually look at this, you can see that this logarithm is half the distance of this one, of 4. So that's all there is to it for logarithms on how to do multiplication and division. You just subtract. But there are other scales on here. I'll blow this up in a minute. There are the regular scales, which are the C and D, which are these. This scale that goes from 1 to 10. And then there's the scales A and B. Let's get a little bit closer on here. Those are actually the square root tables that you find the square roots for. And if you look at this, this scale is 1 to 10, and it's half of what this one is. So if you want to do the square, 2 squared is 4, 3 squared is 9, and of course it works the other way. The square root of 2 is 1.1, and this is 3, this is 4, I covered it up, and then this is divided by 10, so it's 1.41, and you have to estimate what is looks like it's halfway in between these two, so it's 1.415. So that's what I blew it up there. You can see it's 1.4. It's right there between it's 1.4. Actually, if you figure it out, we're off by a little bit different. That last digit's not quite right. This is the other half. The other half, of course, is 10 to 100. And so the square root of 25 is 5. And if you look on this slide rule, this actually has a cube root scale. So it actually has 3 scales, 1 to 10, which other offer, and then 10 to 100, and 100 to 1,000. So the cube of 1,000 is 10. This is my K&E. It's made in the US, and it was actually my brother's slide rule. He was awarded it as a top student as a senior year in high school when he was going to go on to engineering. And I inherited it and used for my first 4 years of school. You notice I said my first 4 years. I didn't graduate in 4 years. If you notice on this one, it's got 13 scales on one side and another 13 scales on the other side. So there's 26 scales altogether. And up here, if you notice, it's got 2 square root scales. If you look at this, instead of having it, like the other one, they made it long. On this one, they doubled it. So they have 2 slide rules, two scales that spend the whole length of this, and then it repeats itself again. So it's actually like going from half to 4 times as long, which means it's more accurate when you take that square root. So you can see up here that this is just not quite touching the 5. So you could interpret that as 1.414, or you could actually say it's 1.415. I think this slide wheel might not be quite adjusted right. You can see that you've got all these screws, whatnot. You want to make sure that all of these scales and everything are all lined up. And you might notice over here, my brother broke this slide rule. He epoxied it together. It's still good 50 years later. I can't believe that. When you're working with the slide rule, you're talking about working with basically 3 significant digits. And hardly anybody talks about significant digits anymore because your calculator's got 10 digits and nobody talks about significant digits. But in engineering, and actually most engineering even today, we're really only dealing with 3 significant digits. Even if you got all of those other numbers at the end really aren't significant. They're the numbers that you really are probably pretty good. I mean, for instance, on this one, you know that 1.41, we're pretty sure about that. We don't know about that 4th one. Is it 4 or 5? But one of my structural engineering professors decided to give us a question. And when we figured it all out, when you got through, you had to divide something, a number like this, 12 to the, about at 0.0005 and divided by 3,000. You can't do it on a slide rule because you can only get 12.1 and then you can't get past that. And so everybody's looking at it, they're rechecking, what did I do wrong here? I can't figure this out. And so nobody got the problem right. The next day when we're looking over the problems, the professor comes in and he says, don't you guys remember the Taylor series expansion? And I'm going like, no. And if you don't remember, this is what the Taylor series expansion is. And it's not something that's that easy to figure out, especially during a test in the structural class, I would argue anyway. So anyway, I remember reading or studying that when he mentioned that, I said, oh yeah, I can remember taking that in my calculus math class. But I'm sure that when I was taking it, I probably thought, what in the heck will I ever use this for? If I'd paid attention, maybe I would have gotten more than a B in my calculus class. So this is my K&E slide rule in its leather case. And Mac was talking about running over a slide rule. And I ran this over in my Jeep, and I thought for sure that probably broke it, at least where that my brother had fixed it. But when it was the winter, so it was in snow, so maybe the snow helped as well. But luckily, it wasn't damaged. But I was really, what am I going to do if this thing is broken? What am I going to do for a slide rule? This slide rule also has a clip on the back, and it used to have a leather strap, so you could put it on the side and you could walk around. And this was, it was a really geek thing to do. All the engineers on college would have their slide rules. Of course, we didn't know what geeks were back then, but we were like Howard was saying that the Hawaiian Electric engineers had their slide rules. I mean, we were engineers, we weren't business majors. But K&E was the top brand. This one online, a good one, was selling for $4,400. I saw there was another ones for about $85. But they had, this is about the top of the line for K&E. There's a couple other that have a few more scales, but this is just about the top of the line for the K&E slide reels. K&E actually had a patent on these in about the early hundreds, 1910 or something, because you used to be able to take the slide out and put another one in and use more scales. And then K&E figured out that you can put scales on both sides. And then they had this indicator so you can transfer your work from one side to the other. And so they got a patent on it. So everybody else couldn't make slide rules like K&E did. So this was their patent application. Yeah, so they put it on both sides, as I said. And this is my 4 regular slide rules, my collection. This is the K&E. This is my high school slide rule. This is a slide rule that I actually got in Japan in a department store in the 80s, probably about like 1981. And the department stores in Japan have fantastic little stationery stores. I mean, even today you can go there and you can get all the drafting tools you need. You can get scales, you can get triangles, you can get the little templates that you make. And they sell that thing. And I'm sure that I found this slide rule in one of those stationery stores. And I bought it because I knew I'd never be able to buy something like that, just walk into a store and buy it again. And then this top one here, I'll talk about in a minute here. And of course, this one over here is my circular slide rule, which I thought that was cool. I got that one when I was in college. I actually have the case and the instruction book. And I think I found one of these online. They were selling for about $50 or something like that. But it sounds like they're not that hard to get a hold of. But the thing about it is it's smaller but it's about 4 inches in diameter. But the scale, the C and the D scale, actually is about 11 inches long. So it's a little bit more accurate than these other bigger slide rules. This slide rule is made out of bamboo. It's a Japanese slide rule, and it's made out of bamboo. A lot of slide rules were made out of wood, but wood can swell and contract. And so, if you get your slide rule and you're trying to get to adjust it, and then all of a sudden it slips, it's hard to use. But I think the bamboo slide rules swell less, and they're easier to use. I think I got that one at the yard sale someplace. Why did I say the slide rule took us to the moon? There are a lot of computer engineering for the control module and actually getting the flight path and how much fuel this rocket needs and how it goes through, the atmosphere is disappearing. So it's very complicated problem which computers can solve. But what's about all this civil engineering work and this big tractor here and this structure here as well? That wasn't designed by a computer. That was designed all by slide rules. This is a Johnson Space Center south of Houston, Texas. This was built in the 60s, this huge campus. And I can tell you, this was not done with computers. They didn't have AutoCAD back in the 60s. All of the engineering and whatnot that takes to put this whole facility together was all done by slide rules. When I was in the 70s, when I was in the Navy, I used to do my own drafting. I joined an offshore company in 1980, and they were doing ink drawings, and they used stencils to do the lettering. And they did beautiful drawings. You would have thought they were CAD drawings, but it was all done by hand. But in the early 80s, AutoCAD did start showing up, but it took about 10 years, I'd say, before AutoCAD was really used at a lot of civil engineering companies. If you look at this, there's a lot of other support companies all across the nation, and those facilities were all done with slide rules. So that's why I'm saying, and I think most people say that slide rules got us to the moon, because in the 1960s, from Kennedy's time until 1969, when they landed on the moon, most of the calculations were being done by slide rules. So I visited the Johnson Space Center in 1985, and for some reason, I didn't connect Houston with the space program, and I didn't even know that this place was there. But why is it there? President Johnson, Lyndon Johnson, where's he from? Texas. And where does he want his space center? Houston. One of the first handheld calculators in 1972 that Texas Instrument issued. It's 3 years after the moon landing. And it basically only has multiplication tables and a percentage there. Computers in the 60s were huge. This is an IBM 360 mainframe, and it's probably less powerful than our PCs are today. And there's a good movie about these 3 Black women who were mathematicians, and they actually were critical to NASA doing all of those calculations. NASA had gotten an IBM 360 computer, and according to the movie, they didn't know how to use it. And these 3 women came along and straightened them out and got it working, did all the calculations for the trajectory and how to put stuff in orbit and all of that stuff. So it's a good movie to watch called Hidden Figures.
1966, Hewlett-Packard sold their first minicomputer. It was the 2116. It was called a microcomputer because it was much smaller than the typical mainframe computers at that time. However, it wasn't designed as a computer. It was designed as an instrument controller. That's because HP was principally an instrument company. Since it was built for on-site data acquisition, it was very versatile and rugged. The first one was used on an offshore research vessel. It cost about $25,000. This mini computer started HP's shift from an instrument company to a computer company. HP then built the world's first scientific programmable desktop calculator in 1968, the HP 9100. It incorporated many of the features that previously were only available on a mainframe computer.
This is the HP 35, and this is the one that killed the slide rule. It came out in 1972, and it's called the HP 35 because it's got 35 keys on it. And when I first heard about it, I said, how can they do sines and cosines with the calculator? And of course they did. And I actually was suspicious that it couldn't do it until I actually saw one. It cost $400, which was probably about $1,300 for me at that time, which is like 3 times my tuition. So I didn't get one. And that was in my 4th year of college. And this thing showed up. And as I said, it could do sines and cosines. In my 5th year, I had to really break down, and the Texas Instrument SR50 came out. And so it was about $200. And that's about $1,300 in today's money, I think. And it got stolen. I had it in my backpack. I went to the computer center. It was behind me. Somebody reached in and took off with it. And I had to come up with the money to buy another one because everybody had computer or calculators by that time. But sometimes once in a while, especially like just when I was looking up my phone on my calculator on my phone, here it is. It's a free app. I had to pay $200 for mine. It was about $1,000 at that time. So I think about that every once in a while. I use calculators. This is inside of a TI, and I never saw the inside of a TI because I wasn't going to risk losing $200 and opening up and breaking it. And I had an interview with Texas Instrument guy. And so I came into the interview room, and he was sitting there. He had one on the table, all in pieces. And I went, oh, is that what it looks like inside? And then I pointed, is that where the microchips are? And he kind of like, no. And later I realized I was probably pointing the keyboard. And then he said to me, he says, you've never taken yours apart? And I kind of said, no. And then I kind of thought I could sense the sarcasm. And then later I was probably thinking, what he was probably thinking was, what kind of mechanical engineer isn't curious enough to actually open up their calculator? I never got a job offer. This is a HP 67 programmable calculator. It's got a little slot on the side, and you can actually put a thin tape on it and actually program it and record the programming on that. I don't think this works anymore. My power supply really doesn't work. And I had to chuck the batteries on it. Were kind of not pretty good. But this was, I really liked HP calculators. They really had the keys themselves. I really liked the way the keys worked. Apollo 13. Why do I say that calculator saved Apollo 13? If you watch the movie, have you watched the movie Apollo 13? You two guys? Yeah, okay. So you remember that they had a problem and everybody had to climb into the landing craft, and the landing craft went around the moon and it was coming back. And because they had the extra weight, they were off course. But before all of that, they had to close down the command module. And when they did that, they had to turn off the guidance computer. And the guidance computer is tied into the gimbal device. They have your camera that walks around, they have the gimbal. Well, they had a gimbal in the spacecraft, and the computer was tied to that gimbal thing. And they had to transfer all of the data to get the coordinates of it. And they had to transfer it they had to check the calculations with their slide rules. So these guys have their little 16 slide rule. They're checking it in the space. They're actually checking it on ground, and they're comparing the numbers. And if they don't get the numbers right, they're going to be lost in space. So that's why I say the slide rules saved Apollo 13. And these two pictures up here are actually from the movie where they actually show them using their slide rules to do the calculation. Okay, the quiz. Here's the quiz. When did I get my first slide rule? From my brother, but what year? 1967. All right.
All right, this was a wonderful presentation. You lived through the history. Thank you for that very interesting history.
Officially, our meeting is adjourned.
Engineers and architects of Hawaii welcome your comment on this program and any of our recent programs. We encourage your direct participation in this community outreach. So please email us your comments and ideas at eahawaii@gmail.com.